Hello, everybody. Welcome back to another edition of Bed Talk, TED Talks from my bedroom. So, what are we talking about today, and kind of where are we going here? So, let's just kind of remind ourselves what we were doing in the past couple of sections here. We have been trying to find basically the answer to this question. If I go along a curve in a vector field, this integral right here tells me how much work it takes for me to move an object or along the curve C in a vector field F with a parameterization R. That's what that tells me. And so I want to find out how much work it takes. Now, what we saw last section, which is pretty cool, is that if I have some very specific types of vector fields, mainly a conservative vector field, if I have something like this, where I have a function, a potential function, the gradient of that is equal to my vector field, then what I could say is, okay, well, this thing here can then be evaluated f at my endpoint and my potential function at my endpoint and my potential function at my starting point. This was a fundamental theorem of line integrals. And this allows us to really calculate things very quickly, especially if we have some type of function like this. We can kind of see this here. Now, where do we go forward here? There are hopefully some interesting types of curves that might be able to help us out, and there's many different types of ways we could evaluate this. We saw in the past, we've seen a couple ways. One, just parameterize the curve and go for it fully, as we saw in section 16.2. If we have a conservative vector field, we can actually evaluate this very, very quickly by just finding the potential function and evaluating that at the beginning and end point. And the last thing that we're going to now tackle, the last way we're going to be able to try to solve this, is with a very specific type of curve. And that type of curve will be a closed curve. And we're going to use Green's theorem to attack it. So what I'm going to say here is this can be for any vector field F, any vector field, not even conservative. It could be for anything here. Let's assume I'm in 2 dimensions here. So I have a vector field F here that's PQ. And I draw this curve here in this direction. And I start and end at the same point. So this curve C, we're going to call this a curve C, we have to be closed. Okay? It has to be a closed curve. And more importantly here, we know that this is highly dependent on the direction that I'm going in. So what I'm going to say is that this curve has to be positively oriented. So what do I mean by positively oriented? Positively oriented. So what am I saying there? That means in just 2 dimensions, it means that I have to go counterclockwise. So I have to go in this direction here. I'm going counterclockwise. If I'm not going counterclockwise, I can flip my direction and then negate everything. It's very important that we'll do that. We'll talk about that in a little bit. But I need to be closed. I need this to be positively oriented. I also need P and Q to be continuous and have continuous derivatives inside my domain. Basically, you need F to be continuous. F needs to be, more specifically, P and Q, they're your components. P and Q continuous in my domain D here. In this inside of here. Now, in D, I'm going to call the boundary of this domain D C. That's what I'm going to kind of going on. Whatever C encloses, that boundary is now going to be enclosing my domain D. All right, that's what I'm going to say here. So if I'm going on a closed curve, and I want to evaluate how much work it takes for me to move an object around this point. You might say to yourself, how is it not 0 if I'm in a closed curve, right? Well, there are some types of vector fields, for instance, a whirlpool or some rotation field, where I'm always going with the vector field, or I'm always going against the vector field here. So this is not going to be a non-zero answer for all vector fields. And so to evaluate this might be a very complicated thing. This might be a really interesting closed curve, but what we're going to be able to do now is kind of relate back what this actual integral means now. What does this integral mean? It means work. And we're going to be able to take this and convert it into an area integral. And that's what Green's theorem says here. So Green's theorem says, Green is a very, very famous mathematician. And people didn't actually realize, he wasn't extremely famous, but he came up with some of these random theorems, especially when he was working in electromagnetism. And somebody found this one day and went, oh, that's kind of a cool thing to do. So Green's theorem has to have all of these stipulations. I need to be in a closed loop, curve C, with a bounded domain D. Okay, my curve C is bounded by my domain D. Has to be positively oriented. If I'm not positively oriented, I just change the direction and negate the entire answer. And P and Q must be continuous inside of D here. Must be there. So Green's theorem says, well, if I want to evaluate f dot dr, as a reminder, this can be written as P dx plus Q dy. This is the same exact thing here, okay? This is the exact same idea. And if I want to evaluate this here, all I do is I can change this curve integral to an area integral. And it's actually going to be a double integral over my domain D of the function Q with respect to X, the derivative of that with respect to X, minus P with respect to Y, dA. And this is what Green's theorem says. And Green's theorem now allows us to convert this, line integral over a vector field into an area integral. And this becomes extremely important because maybe that curve is very tough to parameterize. Maybe this becomes nasty. Maybe P and Q are really, really disgusting. But when we take derivatives, usually things become nicer. And so what I'm going to basically do is I'm going to take this derivative of the one with respect to, in terms of dy here with respect to X, and P with respect to Y. Now, you might say to yourself, well, where have I seen this before? Where have I seen Qx and Py? Well, as a reminder, so the test for conservativity of a vector function, of a vector field, is actually just seeing if Py is equal to Qx. That is a test of conservativity. And so what's interesting here is if a vector field is conservative, these two things would be equal to the same thing. And therefore, if f is conservative, we then find that this integral is always 0 because Qx is equal to Py. And so therefore the integrand 0, and therefore everything is 0. Which is kind of nice. So what are we saying here? If I have a closed curve, I can evaluate the area integral. We know how to do that. Chapter 15 was all about that. That's all we did. That's all we did the entire time. So we are going to now try to use Green's theorem to evaluate some of these problems and try to figure out how to actually do this. So let's do a couple problems here to kind of show you how we kind of go about it. So the first one I'm going to do is this integral right here. This integral of C, y plus e to the x, e to the square root of x dx, plus x plus cosine of y squared here, dy, where C is the boundary of the region enclosed by y equals x squared and x equals y squared. Okay, it is the boundary of the region. Bounded by these two curves. So let's take a look at this. We always assume positively oriented if they do not tell us. It's also really important to remember that. So I know what these things look like. These things look like here, y equals x squared, looks like this. And x equals y squared looks like this guy. And so the region enclosed, this curve right here, I will draw this in yellow. This is my region and my curve C. Okay, so we don't say anything specifically. It doesn't say anything about, what orientation we are in. Let's assume we're positively oriented because we're not told. So what we do is we assume that we're positively oriented here. We kind of go backwards like this. We start at this point. So a couple things to note here. One, this is basically saying, right, this integral, another way of saying this is the amount of work done to move an object from along this curve with a vector field of y plus e to the square root of x and x plus cosine of y squared. Now, if we did not have Green's theorem, how would we go about this? Well, we first off can probably see that this is a weird problem at the moment because I really don't have, oh, I think I messed this up, sorry. This should be a squared up here. So that should be x squared cosine of y squared. So first off, these are really nasty equations here. So if I was to go about doing this, I would have to go and parameterize this curve, right? These curves here, and then plug them in. To this, I would have to find the derivative and have to do two different ones because I can't parameterize this curve all in one fell swoop. So this would be very complicated to do. But what Green's theorem says is, okay, well, I have a closed loop here. I have a closed curve. It's continuous everywhere. These functions are also continuous all inside of here. This cosine doesn't matter. The square root of x has to be positive. X has to be positive, and we're always in the positive x domain. So all I have to do now, I'm now going to name this Bob. No, I'm going to name this inside D here. And now I can utilize, because I've satisfied everything, it has to be positively oriented. Positively oriented. Check. Okay. I have a closed curve. It's check. Continuous. Check. If I've satisfied all of those things, I'm able to go forward now. So this is P, and this is Q. And so what Green's theorem allows me to do is it says, okay, well, you can convert this now to an area integral by using Green's theorem. So what I can do is I can take Q with respect to X here, Q with respect to X, minus P with respect to Y dA. And so now this becomes, as you can see, a nice area integral. And now let's try to evaluate this, right? What's Qx minus Py? Right, Qx minus Py. Qx, the derivative with respect to x here, cosine of y squared goes away. Ah, that's really nice. This just becomes 2x. Y plus e to the x here, this P here, this derivative with respect to y is just 1. And now all this tells us is this horrible integral, because of Green's theorem, becomes just the area, an area integral with the function 2x minus 1 of this domain. And so now we're back to 15.2, right? We just need to find the bounds for this. So let's try to do this then. What are the bounds here? This probably, you can do this either in the type 1 or type 2 region, because it can work either way. I'm going to integrate with respect to y first. That just seems at least reasonable to me. If I integrate with respect to y first, the first thing I hit is the y equals x squared. So it's going to be below. And then I'm always exiting from the region of x equal to y squared. If I'm exiting from the x equal to y squared, I need to have this as a function, as y equals a function of x. And we can do this by saying, this is just y is equal to plus or minus the square root of x. But as a reminder, this is the positive branch, so we just take the positive part here. This becomes x squared to the square root of x. And lastly, we come up with our bounds for x. These guys intersect at the point 1, 1. So this means that x will go from 0 as my lowest point to 1. And now all I do here is I just evaluate this integral. This becomes the double integral. The first off, we're integrating x squared to the square root of x is 0 to 1 of 2x minus 1 dy dx. And this is not too bad now. This becomes 0 to 1. There's no y here, so I just gain the top part minus the bottom part. So this becomes 2x minus 1 times the square root of x minus x squared dx. Okay. A little bit unruly here, but we can make it work. This becomes 2x to the 3 halves, the first one. The next one becomes 2x to the third. This becomes the square root of x, and this becomes x squared. And we can't combine everything. Woohoo! Okay. This integral here, x to the 3 halves, will then become, 2/5 x to the 5 halves. So that would become 4/5 x to the 5 halves. Kind of pulling that down. Yep, that makes sense. Minus, this becomes x to the third. This over here I'll have a minus sign again. This will become 2/3 x to the 3/2. And over here, this becomes x to the 3rd over 3. Oh, sorry. I realized that this integral is wrong. This one is just 1/2 x to the 3rd. And evaluating this now between 0 and 1. Well, we can do this. I only have to care about the 1 here. So this becomes 4/5 minus 1/2 minus 2/3 minus 1/3. And this is some number here. This will come out to be, if I do this by 10, this will be -10, -1/10. Over here, this will just be a -1, so -11/10. That's my answer. So what did we do here? What did we do? As a reminder, we saw this integral. It was horrifying. It was pretty bad. We're trying to find the amount of work it takes to move an object along this curve C in a positively oriented manner. And we saw that this curve was, in this case, it was just, bounding a domain. And what we can do there is, if I'm positively oriented, my curve is closed, and I'm continuous inside my region, these are all continuous inside of my region, then what I can do is I can convert this to an area integral by doing qx minus py. Now, I just kind of want to say something like, why does this work, right? Why is this here? Well, what does it say? Well, it's kind of saying, it's kind of paying the price of how much this vector field is not conservative in some way, right? Because if it's conservative, qx equals to py. This ratio, this kind of subtraction here kind of says, how far away from being conservative are you? And that's the price you have to pay when you integrate the area. So that's kind of what we're doing here. And sometimes this becomes very, very kind of just complicated. But I hope you'll be able to see that with more and more applications of Green's theorem here, this becomes really, really interesting. Let me just do one more example for you here. And then what we're going to do is kind of step back and kind of look at what we just did for the last couple of sections and kind of make a schematic. Because I think it's really important, because we're having so many of these techniques, you don't know when to use them. So how can we make that schematic? So let's do that. So this next problem, the last problem that we'll do here, and then we'll kind of make that schematic, is this. So I want to just point something out before I write this down. Yeah, actually, I can do this. Sorry. Plus x squared times y plus 2x dy. This is my curve. So this is a reminder, this circle here, when you see this integral, this assumes positive orientation. So if you see this circle inside of this integral here, this usually means positive orientation. So what this tells me, it's kind of interesting, is it says where this curve C is any curve that bounds a domain D with area 10. Huh. Okay. Kind of a weird question, right? It's kind of weird. But let's kind of think about this through. Let's try to think this through. So, okay. So a couple of things. I look at this integral. Again, this is a work integral. I have a positive orientation for my curve C. C is any curve that bounds a domain of area D with an area of 10. Okay, so I see here that it's any curve that bounds a domain. So we know that it's closed. We know we're positively oriented. And we have to assume that because these are all polynomials here, we're going to be continuous everywhere. So what's pretty nice is this can just say, okay, well, why don't we just take Green's theorem? I've satisfied everything. I've satisfied being closed. I've satisfied being positively oriented. And I've satisfied just being continuous everywhere because I have polynomials. So as a reminder, this is P and this is Q. So again, what we do is this becomes the double integral over my domain D, which I'm being bounded by this curve. And we will get Qx minus Py dA. Now, what is Qx here? Qx here is going to be 2xy plus 2 That's qx, right? I take the 2 down. And then I subtract this from my p sub y, which is going to be 2xy, the dA. I see that these two 2xy's kind of cancel, and this becomes the double integral of d times 2dA. Now, what does this tell me? Well, if I factor out the 2, this just gives me the double integral of dA. Now, what is this thing? This thing is actually just the area of my domain D. That is the definition, not factorial. But you get what I'm saying. I'm just very happy. Area of D here. So what this says is, okay, all this matters here is in a safe sense, to find out how much work it takes to move an object here, it only is dependent on the area of my domain D. I know my area here is 10. This becomes just 2 times 10, or 20. And what's important here to note is I have done nothing to parameterize my curve. This could be any curve if it bounds an area of 10, which is kind of amazing. And what's interesting about this exact, this here is that if I just tell you how any curve that is closed in this vector field PQ, any curve that's closed, if you give me the area of that, I can tell you how much work it is just by multiplying it by 2, which is pretty awesome. And so this is why Green's theorem can come really in handy. Because I say any curve that bounds an area of 10, you might go, how do I even come up with that? But it comes from the fact, right? You have that this is kind of the form. This is why Green's theorem is so helpful to kind of do this. So that's at least a couple of important things about Green's theorem here. Now, I want to take a step back and kind of overview and kind of say, okay, well, we have all of these techniques, right? We have Green's theorem. We have using conservative vector fields, right? We have, just parameterizing the curve and all. And it might be very complicated and very, very convoluted because we have all these different techniques and you don't know which one to use at one time. And so what we're going to do right now is I'm going to make a flow chart. Because there's really 2 questions you need to ask yourself to figure out what technique you need to use. 2 questions are, do I have a closed curve? Is my vector field continuous? Okay. So this is what I'm saying here. So how to solve, it's basically how to solve f dot dr, or it's also the same exact thing as saying, right, p dx plus q dy, where f here is just equal to pq. These are equivalent. These are the exact same thing. Okay. How do we solve this? All right. The first question you always ask yourself, I always like to ask myself here, is my vector field conservative? Okay. So the first question you ask is, I can't spell is, that's a bad start. Is f conservative? I.e., it's py equal to qx. Okay. There's 2 options. I hope you'd agree. Yes or no. Okay. The next question you always ask yourself after this is f conservative? Yes or no? Okay. The next question you ask is my vector field, is my curve C closed? Okay. Is C closed? Is C closed? We could even do like a Punnett square here if we wanted to. I'm just realizing now, but I like this flow chart a little bit better here because it's kind of the 2 questions you always want to ask yourself. The 2 questions we always ask ourselves: is f conservative? Is C closed? Okay. Let's assume now. Let's go for either way. If f is conservative and C is C closed, okay, there's 2 options, right? We could either say yes or no. All right, what does this mean? If I have a vector field that is conservative and C is closed, I have a closed loop, how much work does it take to me move an object around on this curve? You can see from Green's theorem that Qx would be equal to Py if I have a closed curve, and therefore this entire thing will be 0, right? So therefore, the answer is always 0. So if you answer those two questions, F being conservative, C being closed, the answer is always 0, period. End of story. Do something else fun. That's it. The next thing, if F is conservative, cool. C is not closed. Okay, well, what I know I can do then is use the fundamental theorem of line integrals. Because all I have to do then is evaluate what happens at the end and what happens at the beginning. So I will use the fundamental theorem of a line integral. And again, this says that this integral then could be equal to phi at b minus phi at a, where f is equal to a potential function, right? Something like this. F is equal to some gradient here. I can evaluate it at the beginning and the end point. So this is actually pretty nice. Right, so what we do usually in this case here is we would have to find our potential function and then evaluate what happens at the beginning and the end. This also can show you here that if I have a closed curve, A and B are going to be the same. So these just cancel out and I'm going to be left with 0 anyway. So this kind of also shows you that too. Green's theorem and the fundamental theorem of line integrals both show you that I'm going to get 0 for this part. Here, it's not necessary. But again, this means I'm independent of my curve. My curve does not matter in this case. It just matters where I start and where I am. Now let's go into the more bummer cases where you don't have a conservative vector field. But I still want to find this. My next questions are, is C closed? Let's say C is closed. If C is closed and I don't have a conservative vector field, well, I know for a fact then that I could utilize Green's theorem because I have a closed curve, so I could just evaluate the area inside. So this becomes Green's theorem. And again, this means that I have C, f dot dr will just be equal to the double integral of qx minus py. Okay. So this is what that says. This says that, okay, I have Green's theorem here. I can evaluate if I have a closed curve. If I have a closed curve, I know this is going to be just qx minus py, and I evaluate the over my area domain. How about if no? Well, this is the worst case scenario. If f is not conservative and I don't have a closed curve, I do have to go through the whole process of parametrization. I do have to kind of go through this process. You must go through full process. Sad face. And what does that entail, right? This means that I would need to go f dot dr would be equal to, parameterizing my curve. I would evaluate then my vector field at my parameterization, and I think the dot product with the derivative, dt. So, or in this case, right, parameterizing this and then doing x prime or y prime there, depending on which one you have. But it's kind of the same exact idea, right? So if I have to go through the full process, it's fine. I just have to parameterize my curve C and go through that. This is the worst case scenario, right? That's the first thing we learned, actually. Every single other one of these is just a really specific case. If I didn't have a conservative vector field and I did not have a closed curve, I just have to do this. This will always work regardless. This will always work regardless. These three other processes over here, these three other kind of issues and techniques, are just a different way of evaluating it. This will always work, period. This might be very, 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 very taxing. That's the issue. And so these other techniques might become very, very handy. Okay, so this is, I hope this schematic kind of helps you out here, kind of see this. You can also come up with a Punnett square, right? Saying if I have conservative or closed, right? If I kind of do this thing, I'm just realizing that, right? So if I have, a conservative and I have closed, and I have yes, no, this one is 0, right? This over here is the fundamental theorem of line integrals. Because I have, oh, sorry, wrong way. My bad. If I'm conservative, and it's not closed, I can use the fundamental theorem of line integrals. There are line integrals. If I'm closed but not conservative, I can use Green's theorem. And then over here, if I have nothing and nothing, I can't really do anything. I have to go through full process, full parameterization. That's kind of what I do that. There's two ways you can kind of look at it. You can look at it through this flow chart, or you can kind of look at it through this Punnett square. If there's some biologists out there and that like genes, have a ball with that. Okay, so I hope this kind of helps here, kind of lay out what we do. If I have Green's theorem though, the goal here is just to take qx minus py, if I have a closed curve, making sure it's positively oriented. If it is not positively oriented, what we do is we just put a negative sign out front here. We just negate the entire thing because we know, as a reminder, and this is a really important reminder here, that if I have something, if I have a curve and I want to go the exact opposite way, here I just negate the entire object. So if I want to go the exact opposite way, I negate everything. And so then I could do that. Make sure that happens. Okay, I think that's it here. I hope this makes sense, and I hope this video kind of helped you out, kind of visualize everything we've been doing. Because now what we're going to go into after this is we're going to be solving these types of integrals over vector fields, but they're going to come more over surfaces rather than curves. And so we have to kind of think about what that means, but we'll talk about that soon. I hope this makes sense. If you have any questions, let me know, and I hope you have yourself a fantastic day. Hope you're staying safe.